Today we'll be continuing our video example series for Chemi 330 with our fourth example, a derivation of the continuity equation in Cartesian coordinates. The approach starts with a generalized mass balance. We draw a control volume in the Cartesian coordinate system with sides of lengths delta x, delta y, and delta z. Our velocity in the x direction enters at v sub x and exits at v sub x plus delta x. Similarly, our y velocity enters the control volume at v sub y and exits at v sub y plus delta y. And the z component of our velocity enters at v sub z and exits at v sub z plus delta z. This setup will allow us to perform our mass balance. We begin in the x direction. Fluid enters through the highlighted face on the left, which has dimensions of delta y by delta z. It then exits through the highlighted face on the right, after traveling a length delta x. We can examine the y direction in the same manner, where fluid enters through the bottom face with dimensions delta x and delta z, and then exits through the top face after traveling a length delta y. For the z direction, fluid enters through the front face with dimensions delta y by delta x, and exits through the back face after traveling a length delta z. The general form of our mass balance is that the rate of mass accumulation is equal to the rate of mass in minus the rate of mass out plus the rate of mass generation. In this case, we'll assume that the rate of generation is 0, and we can represent the rate of mass accumulation as delta m over delta t. We can modify the left-hand side of this equation by recognizing that mass is equal to density times volume, and that the volume of our control volume is delta x times delta y times delta z. Substituting gives our rate of mass accumulation as the change in this term divided by the change in time. Now we need to determine the net flow in each direction. Beginning with the x direction, we can write our mass flow rate in as the density times the entering velocity times the cross-sectional area of the face through which it enters. We get a similar term for our mass flow rate out, except we now use the exiting velocity. Our net flow is then the difference between these two terms, which is the product of density, the entering velocity minus the exiting velocity, and the area of the face through which they flow. We can repeat this process for the y direction, where the relevant area is now delta x times delta z, and we use the entering and exiting velocities in the y direction. Again, we take the difference between our mass flow rates. This gives us a net flow in the y direction of density times the entering velocity minus the exiting velocity times delta x times delta z. Finally, we repeat the process for the z direction, writing our mass flow rate in, our mass flow rate out, and taking the difference between the two to yield our net flow in the z direction. Now we can combine the terms that we found with our rate of accumulation equal to the sum of the net flow rates in each direction, each of which we just found an expression for. We can simplify this expression by dividing by delta x, delta y, and delta z, which gives us terms that each depend on the change in only one variable. Because each term depends on the change in a unique variable, we want to take the limit of this expression in regards to each. We take the limit as each denominator goes to 0, and each limit applies only to the term with the relevant variables. These terms now look like the definition of a derivative, with those on the right-hand side negative, of course, because we are subtracting the exit condition from the initial condition. And so we can write each term as a partial derivative in terms of one variable. And our final step will be to simplify, yielding the Cartesian continuity equation.